RSA. An example of public key cryptography is RSA. It was first described in 1977 by three men, the RSA coming from the first letters of their surnames, Rivest, Shamir, and Edelman. RSA steps to creating keys. The first step is to select two very large random prime numbers, P and Q. Here, we will use smaller numbers to make things easier to explain. P equaling 11, Q equaling 5. To calculate RSA modulus n, you multiply P by Q. 11 times 5 equals 55. The second step is to calculate the totient function. This means the totient of RSA modulus is P minus 1 times Q minus 1. So 11 minus 1 times 5 minus 1 equals 10 times 4 equaling 40. Now we select the value from the key E. E must be smaller than the totient of RSA modulus and also coprime to RSA modulus. Coprime means the two numbers don't share any other factors except for 1. Our options are 3, 7, 9, 11, 13, 17, and so on. We will be using 7. We need to calculate the decryption key with our private key, D. We will be using this formula to calculate D. This means D times 7 equals 1, modulo 40. We will use an Euclidean algorithm to solve this. We put 40 on one side of the equation and find out how many times 7 goes into 40. The answer is 5, remainder 5. Now the 7 moves to the other side of the equation. The remainder number 5 moves to the other side. How many times does 5 go into 7? 1, remainder 2. Now the 5 moves to the other side of the equation. The remainder number 2 moves to the other side. How many times does 2 go into 5? 2, remainder 1. We stop at the last non-zero remainder. We then use the extended Euclidean algorithm. We start with 1 because that was our last result. From above, we know 1 equals 5 minus 2 times 2. We then make successive substitutions for the remainders from the Euclidean algorithm. So we now substitute the 2 from this line. So 1 equals 5 minus 2 times 7 minus 1 times 5. Extending this equation gives 1 equals 5 minus 2 times 7 plus 2 times 5. So combining common values, 1 equals 3 times 5 minus 2 times 7. Now we substitute 5 from this line. So 1 equals 3 times 40 minus 5 times 7 minus 2 times 7. Extending this equation gives 1 equals 3 times 40 minus 15 times 7 minus 2 times 7. So, combining common values, 1 equals 3 times 40 minus 17 times 7. We now have the two original values, 40 and 7. The important number is in front of our encryption key, 7. This is minus 17. If this was a positive number, this would be our decryption key. But because this is a negative, we calculate D equals minus 17 modulo 40. So D equals 23, which is our decryption key. The result of this is Bob knows N and his public key E, which he can distribute as he wants. Alice can use N and E to encrypt the message for Bob. Bob can decrypt the message as he has the only decryption key D and the totient of the RSA modulus. RSA encryption. Alice wants to send Bob a message. Hide. This is the equation to encrypt each plaintext letter. These are the keys from the steps shown previously. Encrypting H. The numerical representation for h is 7. C equals m to the power of e modulo n. M equals 7. E equals 7. N equals 55. So C equals 7 to the power of 7 modulo 55. C equals 28 modulo 55. This is our first ciphertext. 28. Encrypting I. The numerical representation for I is 8. C equals m to the power of e modulo n. M equals 8. E equals 7. N equals 55. So C equals 8 to the power of 7 modulo 55. C equals 2 modulo 55. This is our second ciphertext. 2. Encrypting D. The numerical representation for D is 3. D equals m to the power of e modulo n. M equals 3. E equals 7. N equals 55. So C equals 3 to the power of 7 modulo 55. C equals 42 modulo 55. This is our third ciphertext. 42. Encrypting E. Numerical representation for E is 4. C equals m to the power of e modulo n. N equals 4. E equals 7. N equals 55. So C equals 4 to the power of 7 modulo 55. C equals 49 modulo 55. This is our fourth ciphertext. 49. RSA decryption. Mark receives the ciphertext. He uses this formula to decrypt the ciphertext. Decrypting 28. M equals C to the power of D modulo n. C equals 28. D equals 23. And N equals 55. So M equals 28 to the power of 23 modulo 55. M equals 7 modulo 55. 7 equals H. This is our first plain text, H. Decrypting 2. M equals C to the power of D modulo n. C equals 2. D equals 23. And N equals 55. So M equals 2 to the power of 23 modulo 55. M equals 8 modulo 55. 8 equals I. This is our second plain text, I. Decrypting 42. M equals C to the power of D modulo n. C equals 42. D equals 23. And N equals 55. So M equals 42 to the power of 23 modulo 55. M equals 3 modulo 55. 3 is D. This is our third plain text, D. Decrypting 49. M equals C to the power D modulo n. D equals 49. D equals 23. N equals 55. So M equals 49 to the power of 23 modulo 55. M equals 4 modulo 55. 4 equals E. This is our fourth plain text. Now we have a plain text message, hide.